Thank you, Tom, for this very kind introduction, and good morning, everyone. Did you ever feel that the insights that you are designing as a part of your exploratory data analysis is not enough? Or maybe the decisions that you took on the back of these insights were suboptimal to some extent? If any of those applies to your team or to you, then I think you can really benefit from this talk. What I want to discuss today is how we can improve insights utilizing the causal inference methods. This talk is divided into three main sections. So first of all, we will start with a very, very gentle introduction, and we will discuss why do we do insights and what is the relationship between correlation and causation and how to differentiate between these two. Next, we'll move on to discussion around two causal inference methods: propensity score matching and the regression discontinuity. And I've chosen those two causal inference methods, first of all, because we have only 40 minutes for this talk, and second of all, because I think these are two very different approaches to the causal inference. So propensity score matching, the biases the data on a user level, and the regression discontinuity design, the biases the data on a metric level, on a more aggregate level. And finally, we'll wrap up this session with the discussion around limitations of the causal inference. And I think the main takeaway from this session, which I'll mention right now, and I'll also mention that by the end of this session, is that we cannot really replace the randomized control trials with the causal inference, but we think, that is like Booking.com thinks, that actually using causal inference can help us to make better decisions, and it may help us to drive a higher business value. So first of all, why do we do exploratory data analysis? Why do we do insights? And it is a very, very simplified value complexity matrix that most product managers, most data scientists use in order to prioritize their workflow. On the x-axis, we have the implementation complexity, and on the y-axis, we have the business value. So when it comes to deciding about which project we should do next, which incremental improvement do we want to do next to a particular data science model, then we usually assess it using those two dimensions. So first of all, we have implementation complexity. And usually you can assess the implementation complexity on your own. You can use your own experience, you can use experience of your company in order to estimate like how much effort it will take to complete a given project or in order to make an incremental improvement to your model. So this is doable. But on the other hand, we have business value. And it is much harder to estimate. In fact, Booking knows that like usually the improvement in accuracy of your models doesn't translate one-to-one into the business metrics. And what we can do is we can use observational data and try to like do the opportunity sizing and approximate the business value. However, the regular exploratory data analysis and the insights that we do are usually based on the correlation rather than the causal analysis. And because of that, we may make, as a consequence of that, we may make suboptimal decisions. So ideally, we want to target those two easy wins and long-term projects. But if we were to use just simple correlation analysis, then it may not always happen. We may miss some opportunities. And as an introduction, again, what is the difference between correlation and causation? So let's imagine that we exist in a world that includes only three elements. We have sun, we have happiness, and we have crime. And the hypothesis that we're trying to test is, let's say that there's a positive correlation between happiness and crime. And if we operate in this very simplified version of the world, and if we were to do a simple correlation between happiness and crime, then probably we would record the positive correlation coefficient. And it is because like when we have a sunny weather, it makes people more happy. When we have the sunny weather, it also increases the crime. And if we don't account for the fact that there's like another element in our universe that is sun, if we do not condition on that when we do the correlation analysis, then we can actually confirm our hypothesis, and we may arrive at the decision that yes, happiness increases the crime, and because of that, we should reduce the happiness of people in order to reduce the crime rate, right? And that's what we're trying to do with the causal inference. We try to account for the things that exist in our universe, and we try to debias our data in order to make optimal decisions. This is a very, very simple pyramid that shows us the trade-off between the accuracy and the cost of modeling. So of course, our golden standard is our randomized controlled trials. This is the experimentation. Ideally, we would test all of our hypotheses with the experiments, but unfortunately, they're very costly. We are unable to run them all the time. Then we'd need to develop all the models, and this is just simply not feasible. Then on the bottom, we have correlation analysis. So let's say this is just a simple exploratory data analysis that includes some heat maps, contingency tables, and so on. And it is very cheap. Usually, most of the data scientists do that at the beginning of the project in order to get the sense of data and in order to navigate the project roadmap. However, as I have shown on the previous slide, this correlation analysis may be biased, and because of that, we may make suboptimal decisions even at the point of the exploratory data analysis and designing the project roadmaps together with the PMs. And that's why what I propose is that we should use the causal inference in order to debias the data. But the problem with the causal inference is that it requires some specialistic knowledge. It is more time-consuming. Sometimes it may take 2-3 weeks in order to prepare a good quality causal inference model. And at that point, you might as well just do the simple MVP and run the experiment, right? So instead of that, what we are proposing is that we attempt to democratize the causal inference method. We want to reduce the cost and the entry barriers to the causal inference, and we want to replace the correlation analysis here with the causal inference that can be used both by not only by the data scientists who specialize in the causal inference, but also by the data analysts and the product managers. So let's try to map it into the Booking.com's problem. So one of the main algorithms that we have at Booking.com is ranking, right? And we observe a lot of interactions of our users with the ranking model. And let's say one user, it's myself, I get a given treatment, and for instance, I see this car, which is the top pick, as the top one slot. And just because it is observational data, then we don't randomize across those users who got this treatment and those users who didn't get this treatment. So what we try to do in the causal inference is we try to find another person that have exactly the same characteristics and is most likely to exhibit similar behavior. And we try to match these two users together to create this sort of synthetic user. Then we take simple difference in the observed outcomes from receiving this treatment, and this is how we debias the data, and this is how we can test the hypothesis itself. This is a more formal definition of what is bias and just some mathematical notation that might be useful later on. So first of all, let's define the potential outcomes as y, z, where z belongs to either 0 or 1. So potential outcome that a user received a treatment and didn't receive the treatment. Then we define the treatment as d. So d is binary just for simplicity, so you may either receive a treatment or not. And generally, it is true for the observational data that potential outcomes are not independent from the treatment. And what we're trying to achieve with the causal inference is that we try to add matrix AX that account for some observable characteristics. And after we account for these observable characteristics, and after we condition on it, then we want to achieve the independence of our observed outcomes from the treatment itself. So I think this really sums up what we try to do with causal inference, right? We assume that we have some observational data, and we assume that we are able to condition on them in order to introduce randomness. And today, I will mostly talk about the average treatment effect on the treated. So it's slightly different to what we usually report when we assess the experiments, when we do the point estimate. So usually, we do average treatment effect. But in that case, what we simply do is we take all the users that were treated, and we try to find their synthetic versions using some sort of using the causal inference methods. So we will only know what was the impact on those users that received the treatment rather than the average user. So let's start with the first exciting model, which is propensity score matching. Bias in our data, like specifically for booking.com, but in general can have multiple sources. And we have a couple of data sets that are available for us that are able to debias, that we are able to account for, and then they debias our data. We have current session data, platforms data, and census original data that are available for everyone. And you can see that these are like different sources of bias that we may observe, such as age, channel from which users came from, whether they use mobile phone, their wealth, country of residence, language, source market, etc. So in propensity score matching, we try to use current session data, platforms data, and census and regional data in order to account for all of these observed characteristics and remove the bias. On a very high level, propensity score matching includes 4 steps. First of all, we estimate the probability that a given user will receive a treatment. Then we use that using the logistic regression model, which is very standard, but like you can use GBM or like any other model which you think may be more accurate. But just for the explainability, we use the logistic regression. Then we match users based on their propensity scores. We compute the difference between these matched users, and then we assess matching quality and sensitivity. Again, as an introduction, you can see this graphical example of what is propensity score matching, what do we do with the propensity score matching. Here on the top, we have like different bubbles, and size of the bubble represent the propensity scores. So like small bubble, small propensity score, large bubble, large bubble, large propensity score. And then we get the treated users. So we extract all the, sorry.
Keep talking.
We extract all the orange bubbles. And what we try to do is we try to match the blue bubbles to those bubbles, to the orange bubbles. And then we take the difference between the observed treatments, and that's our propensity, that is our average estimate of the average treatment effect only on treated users, so only on the orange bubbles. And unfortunately, I think like that's the main thing that I want to discuss today. The causal inference methods in general are very, very limited. I know that in some domains such as like economics, like that's the only thing that researchers can use in order to, because like we cannot experiment on everyone, right? But like they have serious limitations that we need to take into consideration when it comes to assessing the quality of our models. And the main limitation is that we assume that our propensity models, or like in general, we assume that our causal inference models are correctly specified. So we assume that X, so the observable characteristics of the users, are accurate. So first of all, like we may have some noise in the observable characteristics. They may not be representative. And second of all, we assume that we have accounted for all the characteristics of the users that may determine the assignment to the treatment. And there are a couple of things that we can do in order to assess the omitted variable bias on, in terms of like propensity score matching. And we have the sensitivity analysis, and this is probably the analysis that you've read about. If you did the propensity score matching, that is, you try to augment your model by, for instance, adding features that you didn't originally include in your model in order, and then you plot its impact on the average treatment effect on treated, on the confidence intervals, and on the p-value, in order to understand what is the potential outcome of not including enough characteristics in your model. You may also augment your features that are originally in your model by, for instance, increasing the correlation with the dependent variable, and again, you'd plot it against the estimated average treatment effect on treated, confidence intervals, p-values. But I guess this is something that is like widely described in literature, and this is something that we proposed and that we included in our model. So what we did is we created a synthetic feature that to some extent is correlated with the treatment, and to some extent it includes the noise. So for instance, noise 100, it means it's like total like noise, like it doesn't include any correlation with our dependent variable. Then you have noise 90 up to noise 10. So noise 10, for instance, includes 10% of noise and 90% of correlation with your dependent variable in your propensity score model. And later, we add it in an iterative manner to our logistic regression model, and we record its impact both on the ATT, on the confidence intervals, and more importantly, on the coefficient values of other features that we have included in our model. So this plot shows the relationship between the noise level, so noise level of our synthetic feature that was injected into the model, and on the y-axis we have the coefficient value of our other. So this is just one coefficient value, but obviously we do that for all the independent variables that we have included in our model. And what we see here is that at the very, very low noise level, the coefficient value converges like to 0. Basically, if we have like a strong feature, if we inject a strong synthetic feature to our model that is highly correlated with the dependent variable, then it dominates the whole equation. But later on, as we increase the noise level and reduce the correlation with our dependent variable, the coefficient value of other features converges to a certain level, and that is what we want to see, right? If our model is correctly specified, we hopefully would see that earlier on. And this is like just alternative approach to the sensitivity testing of our propensity score model. And also at the beginning, I mentioned that we wanted to democratize this solution. So we wanted to automate it. We didn't want it to be only a one-off analysis, some notebook that will be just like run once, and then like we didn't want just to share this with our stakeholders, and that's all. And that's close the project. We wanted to automate it, and because of that, and not only because of that, it's also a good practice. We did a train test split in order to estimate our model, and we have chosen the model with the highest F1 scores, area under curve, and like with the best confusion matrix. And this is, again, something that is not widely described in the literature, specifically in the econometrics literature. But what we think we should do is also we should do train test splits for the causal inference and econometrics model, specifically because we will want to use this solution also for the other treatment. Like you may say that in that case, okay, you did train test split, so it means that you don't overfit to your observed characteristics, but you still may overfit to that treatment that you have selected and on which you trained your propensity model. It is true to some extent, but well, this is a first step in terms of like democratizing of this model. And finally, we do the matching validation. So I will not focus too much on it. It is just like simple checking that we have the common support between the treatment and control, and that we have balance in features that we accounted for. But this is like a very automated, like you can use it. You can do this plot just using the pre-made packages. And today I wanted to share with you the demo that we have prepared in terms of like how we tried to automate this propensity score matching. And this is our case study. So we simply wanted to see what is the impact of having a zero-rated supplier within the top 5 slots. So let me just quickly play it here. And we did it based on the Shiny app. The Shiny app consists of 4 main sections. So first of all, we have the section that describes the model itself, that have some attachments that might be useful if a given person, like product manager or the data analyst, want to get some intuition behind the methodology itself. And later we have the estimated average treatment effect on treated section. And this is a section where the user can specify the amount of historical data that they want to do in order to estimate that this particular treatment effect. They can inject their bespoke SQL query in here that dynamically links to our Hadoop. And later on, we have the ATT reporting, the PSM model validation, and the matching analysis that allows users to see whether this like automated workflow has correctly specified has worked correctly. And again, this is all based on the synthetic data just for the purpose of this demo. So here in here you can see the distribution of the bootstrap sample. I think here we just did like 5 bootstrap sample, so obviously the histogram doesn't look that great. But later you can see that you can use your own bespoke treatment. You can copy-paste it to the window itself. It will then dynamically connect with the Hadoop. So you define the treatment inside there, and it works on a user level. So we already define user as the experimental unit, and then it links the training data with the treatment data, and again retrains the model and do the bootstrapping, and then reports on the characteristics of the PSM model and the distribution of the ATT. Okay, so that was the demo. And the another model that I want to discuss today is the regression discontinuity design. So RDD is slightly different to the PSM, just because PSM works on a user level. In case of RDD, it works on a more aggregate level, and I just thought that it's a nice overview of why that we can use a different causal inference method for the different use cases. So RDD, you can think about it as a simple pre-post analysis where you observe some metric on an aggregate level, and then suddenly we have a treatment. So for instance, we implement a model full-on for all of our users. We observe some variation in data, and this is not a natural variation in data. This is a variation in data caused by this treatment. And we try to model, we try to account for this variation, and based on this variation, we try to estimate the average treatment effect. And why regression discontinuity is better than the simple difference in means? Well, you can see it here. I simulated this data using quadratic function. On the x-axis, we have date sequence. Y-axis, we have value. And then we have a treatment that occurred around date sequence 50. And what we want to do in here is we try to take advantage of this variation, of this synthetic variation that was caused by us in this data, and we try to model the difference, whether we can observe anything significant that happened to our aggregate metric. And if, let's say, we have a quadratic seasonality in our model, and if we were to do a simple difference in means, so here I fitted a linear regression model with the running variable that takes value 0 before date sequence 50, 1 after date sequence 50, and if we were to do a simple pre-post, then we would arrive at a very spurious correlation, right? We would think that we actually observed a huge uplift in our metric, but in reality, we just have some seasonality, and if we don't account for this seasonality, then we will arrive at the wrong conclusions. And regression discontinuity is a method that involves 4 main steps. So first of all, we conduct AA tests on the residuals of our regression model and check for the stability of the metric. And at the same time, we experiment with different covariates and model fitting. So the first 2 steps are very iterative. Then we estimate the causal impact effect using a predefined set of covariates, kernel weights, and running the linear regression. And simply we do bootstrapping and report the confidence interval of the mean. So let's first focus on the AA testing and modeling, because that's really crucial for this particular model, right? So what we try to do is we try to find a metric that is stable over time, or if it's not stable, that it is explainable by, for instance, seasonality, or by some intercepts such as the Black Friday discount, or some holidays data. And if we find such a metric, then we try to decompose it using linear regression model. And after we decompose it, we take the residuals of the linear regression model itself, and residuals is just the part that is left over after we fit the model. And then we plot these residuals, and we split our date sequence into the pre-post parts, and then we do Kolmogorov-Smirnov test, t-tests, we don't want to reject the null, and stationarity test. And this is just to ensure that our mean and variance are stable over time. And this is a very iterative process when it comes to both modeling and AA tests. They are not, so you should do that both at the same time, right? You try to find a stable metric, you try to model it, you take residuals, you do the t-test, and then it doesn't work. For instance, you observe lots of false positives. Then you come back to modeling. or like you try to find a better metric. So we try different covariates, interactions on pre-experimental data, such as Black Friday, day of the week, trend, Christmas. We then try to explain the whole model, take residuals, and again, we just conduct tests in order to ensure that our model is correctly specified. And I think that's a really nice difference when you compare RDD to the PSM, because in RDD, you're able to actually quantify your omitted variable bias. So you see straight away if you didn't account for some characteristics of your metric on the aggregate level. And that's why personally I prefer RDD, even though it's on it's an aggregate. It works on the aggregate metric level. And like in our experience, we observe also lots of type M errors. So for instance, we saw treatments like that were like +5%, +7%. But in reality, later on, we checked that and they're like not statistically significant. But we still think that RDD in general, like at least it's recommended by me, just because I saw that, just because it is more explainable and just because we are able to quantify this omitted variable bias. Another thing that I recommend is just adding kernel weights. So instead of simple linear regression, I'd recommend doing the weighted linear regression in order to add more weight to the dates that are closer to the switch date rather than the dates that are more far away to the switch date, just because we have more randomness around the switch date, and the more far away we move away from the switch date, the more we rely on the model itself. And this graph just, I guess, emphasizes the fact that the kernel, we need to be very careful with the kernel weights because they may have a very strong impact on the p-value and on the estimated treatment coefficients. And this is just like the regression discontinuity in practice. Again, we have a couple of practical issues such as omitted variable bias, overfitting, unstable metric, and it is much harder to democratize because it relies on the expertise of a user to choose the metric and choose the form of the model correctly. We will try to attempt to democratize this as well, but so far we were not successful just because of this modeling stage. So just to wrap up this session, I think there are a couple of fundamental issues that are linked to the causal inference. I think that the causal inference is much better than the simple exploratory data analysis or the correlation analysis because it removes some bias from our data. But at the same time, we need to be aware of the omitted variable bias and the fact that observational data has its own limitation. And that's why causal inference may not replace the randomized controlled trials, but it may help us to make better decisions at the stage of the exploratory data analysis and designing the project roadmap itself. Thank you.
Amazing, wonderful talk and very, very popular. Okay, we've got some time for questions now. So if you'd like to raise your hand if you have a question, and I'll work my way around. We'll start with the person over here.
Thanks for the presentation. Yeah, thanks for the presentation. I know you talked about that a bit, but regarding the empirical evaluation of the estimation method, do you have do you have a way to do it like robustly to automate that and to make? I mean, I know you talked about that, but to make that part of a bigger production system.
Yeah, I mean that's a really good question because that's what we are trying to do, right? So like with the issue with the causal inference is that it requires a lot of time in order to do that correctly. And even if you spend a lot of time attempting to do an accurate estimation, then it may not work great. So just to come back to this slide, I would highly recommend the paper that was made by Facebook, and the paper is titled A Comparison of Approaches to Advertising Measuring Evidence from Big Field Experiment. So they analyzed 15 large-scale advertising randomized controlled trials conducted at Facebook. And on average, they found a significant discrepancy between the causal inference estimates and the randomized controlled trials. So you can see that even if you're not trying to democratize this method, even if it's done by the experienced set of researchers, it may not be very accurate in terms of like, based on our experience at Booking, I think we observed a lot more type M errors, so the orders of magnitude errors rather than type S errors. And I think that's why we think that it's really hard to design a robust, I think that it's really hard to design the robust model that would allow other users to reuse it. But I think that there's still some value in terms of like attempting to democratize it, because it will still balance some of the observed covariates inside your model. It may not balance anything, right? Everything, right? But you can always validate that the features that you have specified inside your model have been balanced by using the post-experimental analysis. So the major drawback of the approach that I proposed here, specifically with the propensity score matching, is that it relies on a fixed model, right? Like we don't allow users to add covariates inside this model. We just derived this model based on the train test split at the point when we are designing this solution, but we don't really allow users to add their own covariates that they think we need to account for when estimating their treatment effect on the treated that was defined by them. So I think, yeah, that's a really good question, like whether it is possible at all to democratize it. I think to some extent it is possible, but by attempting to democratize this method, you will introduce more bias compared to just having bespoke solution for a particular treatment. And another issue is that sometimes, like if we balance certain characteristics of users, and if we have some omitted variable bias in our model, how do we know that by balancing these features, we didn't introduce even more bias on these unobserved characteristics? I think that's something really fundamental as well. So that's why I prefer RDD, because at least in that case, we can to some extent quantify the bias and quantify the bias of our model with the pre-post analysis on the residuals before we actually introduce the treatment. But with the PSM, we can inject some synthetic features to our model. We can do the sensitivity analysis. We can augment our model. We can add some variance to our model. But at the end of the day, we will not know what is the impact of balancing on observed covariates on the balance of unobserved covariates. But yeah, that's a good question. Thank you.
Thank you. Can you hear me? Well, thank you for the great talk. I think it's really, really inspiring to see that you use the causal inference methods in debiasing exploratory analysis. Just have a question around, for example, let's take the example that you said about the ranking model and looking at the output. I'm just wondering, once you discover the insight, how do you then use that? Do you use that to inform further model developments, like patching up the holes? And then I saw the tools that you fixed that. One hypothesis is that if you show the uncommented cars onto the user, that has a negative impact. How do you discover those hypotheses in an automatic way? Does the tool allow that? So yeah. So
in terms of discovering the hypothesis, it's usually done by the developers and by machine learning scientists and by the product managers / product owners. And we also discover some of this hypothesis based on the correlation analysis, right? So I didn't say that we should totally replace the correlation analysis with the insights and the causal inference. But what I'm saying is that once we have a hypothesis that, for instance, was formed based on the correlation analysis, so maybe we saw that there's a huge correlation between having a zero-rated supplier and the conversion rate. So this is our initial hypothesis. We saw that in our correlation analysis. We saw that it may have a negative impact on our primary metric. And then what we do, we define this treatment more rigorously, and we inject that inside this model. And then once we see that, actually, it may increase our conversion rate, but that by removing this from our data, it may increase our conversion rate by, let's say, 1%. Then we rank it against other hypotheses and estimates from other hypotheses. Then we come back, we prioritize, based on the implementation complexity, and we target these treatments with the highest potential uplift and the lowest implementation complexity. So again, we use it only at the point, we encourage to use it only at the point of driving the product roadmap, rather than we would never, for instance, go full on once we estimate some treatment effect, in terms of we would never modify the model and then go full on without testing this hypothesis.
Thanks for a great talk. In terms of data quality and how much data you've got, can you give an example of where this approach would work well and where it wouldn't work so well?
So usually it works great it works better if there are many users that received the treatment. So it's very similar to really just like regular experimentation, right? Like you want to have like large volume of users that are eligible for a given treatment, and you want to get like many users to receive this treatment, because the more users receive this treatment, the more accurate are your estimates. So yeah, just to answer your question, yes, still volume and the amount of treated users have a huge impact on the accuracy of the predictions.
Yeah. Thanks, great talk. Just wondering if there is any other techniques you've ever used other than RDD and like PSM, for example, like double machine learning or doubly robust estimations, stuff like that?
Yeah, I mean, I used the difference in differences, synthetic control, like instead of the propensity, instead of RDD, and then we used so instead of PSM, we used the IPW as well, but this is just like a modification of the propensity score matching. So yes, we have used other causal inference methods as well, but we just chose those two for this showcase because, I mean, I just chose those two for this showcase because I thought that like they're quite simple, quite understandable, and they show like two different angles of how can we bias the data. And I think like this paper really analyzed like even more potential like causal inference methods, but what they found is like that there's no causal inference method that really performs consistently better than another causal inference method. So I think when it comes to the choice of the causal inference methods, I will always try to design it specifically for a given treatment. That is like, for instance, sometimes you may have a stable metric, then yes, it's great. Like you can use the RDD. But if you don't have a stable metric, or if you want to, if you have a rich data set on a user level, then instead of that, I would just use PSM.
I think I'm next. Thanks for the talk. Love your work. The new sexy type of thing for causality is shape or shapely values. I have a couple of friends that or colleagues that sort of like say, look at this, super cool. And I asked, does it perform better than logistic regression with a really well parameterized model? So I want to know what you think of it. I'm trained as an econometrician, so like logistic regression, love it, but the model has to be right for me. What do you think?
The model has to be what? Could you repeat that?
For sharp or shapely values.
Uh-huh. I mean,
what do you
the
think?
importance, or the feature importance.
Yeah, exactly.
Right?
Like some people use it as, look,
Yeah.
this is causality, and then I'm not. Yeah. What do you think of that?
I mean, I mean, to me, it still sounds like a correlation analysis, right?
Yeah.
So like when you have, like when you just do that using the, let's say, linear regression model like GBM, and then use the feature importance, like it's just a simple correlation, but you add more context to it, because usually when you do a simple like, you know, just like Pearson's or Spearman correlation analysis, then you design heat map and like you don't have a model, but you have these two features, and then you only investigate the correlation between these two features. But when you have a whole like just logistic regression models, let's say GBM, then you assess the correlation of your metric and a particular feature with relation to other features that you have inside the model. So I think, yeah, just to answer your question, I think it's better than the simple correlation analysis, but I would still encourage people to use the causal inference in order to debias their data, because you only add a little bit of context to your model instead of removing the bias. But I mean, I do exactly the same. I also like sometimes when it comes to like quick EDA or like fast insights, I also like just run the logistic regression model like GBM and then check the feature importance. So it is a good technique. Like it may give you more insight into your data. It may help you to form the hypothesis, but it will not replace the experimentation or like the causal inference methods.
Any more questions? Final call? Adam, thank you. That's the most packed I've seen a DSF.
Was it too much?
Round of applause.